Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it: planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, NASA's chief scientist, and this is Gravity Assist. Today I'm here with Lindley Johnson, NASA's planetary defense officer. He's in charge of keeping our homes safe from countless numbers of small bodies and debris that hit our planet or even fly by our orbit. You know, the dinosaurs didn't have a space program, as we say in this business, and it's not a matter of if, it's only a matter of when. And so, Lindley, you're our first ever planetary defense officer. So, for our listeners, what's the difference between an asteroid, a meteor, and a meteorite?
Okay, well, that's a common question that gets asked. It can be a little bit confusing, but the difference between an asteroid and a meteoroid is simply the size. The International Astronomical Union just recently laid out the distinction between the two, and everything that's smaller than 1 meter in size is a meteoroid, and everything bigger than a meter in size is called an asteroid. Now, when a meteoroid or even an asteroid enters Earth's atmosphere, you see this blazing trail across the sky. That's what was seen in ancient times, but they didn't know exactly what it was, and that was called a meteor. Now, once the object passes through Earth's atmosphere, breaks up, and pieces fall to the Earth's surface, to the ground. And those rocks, so to speak, are called meteorites. And those are what scientists like to collect as soon as they can after a fall to do a scientific analysis of what is essentially a free sample return from space.
Right. You know, it's not just scientists. More recently, they looked at a dagger that came from Tut's tomb, and it was iron. And they did the analysis of it, and it turned out it had a certain iron-nickel ratio, which indicated that it was not of Earth origin.
Yeah, that's true. In fact, archaeologists have found a number of artifacts that look like they were made out of meteorites. The iron meteorites are very much able to survive entry through the U.S. atmosphere, and probably to the ancients that was their one source of metal.
Right, and the connection with space and perhaps their religious gods.
Mm-hmm.
Yeah, indeed. All right, getting back to today, what's the first step in protecting Earth from these kind of strikes?
Well, you got to find them first. You got to be looking for them, find out what's out there, what may come close to Earth's orbit, and you need to find them well in advance of any close approach or impact to the Earth, because it will take us time, years in fact, to be able to get out there and do something about them before they become an impact hazard to the Earth.
Is that because they're so small? I mean, they're so much smaller than planets and moons.
Well, that certainly makes it more difficult to find them, but it's just simply the time that it takes to get a spacecraft out, or to get it built first of all, and then to get a spacecraft out to the object to be able to interact with it in some way to change its velocity. That's the main principle behind mitigating an impact, is just simply changing the velocity of the object so that at the predicted impact point in time, the object shows up late.
How are we able to see these relatively small objects? Aren't they largely very dark and black?
Yes, there is certainly a population of these objects that is very dark as coal, so that makes them very difficult to see in the visible part of the spectrum, which is where we are mainly searching right now using ground-based telescopes. But that's one reason why we would like to be able to search for them in the infrared part of the spectrum, because these objects are illuminated by the sun, and they absorb the heat from the sun and then re-emit that heat as radiation that can then be detected in the infrared part of the spectrum. The catch to that, though, is you have to have a sensor that is looking for them in space, because They are so small and dim that the energy can't make it all the way through the Earth's atmosphere. It blocks it out.
Now, we currently have one telescope in space that is in the infrared.
Yes, that's right. We have a spacecraft which was originally called the Wide Field Infrared Survey Explorer, launched by the Astrophysics Division to build up an infrared background of the sky. And it was constantly imaging the sky to build up this map of the sky. Well, we quickly figured out that with all the images that it was taking, we could look for an asteroid moving across the sky in those images, and it became a prototype capability, so to speak, for an infrared telescope. After the astrophysicists were done with it, the Planetary Defense Program here at NASA took over operations of the spacecraft, and we've made it a full-time asteroid hunter and for characterization of them as well, figuring out their size.
You know, with all the telescopes now we have on the ground that are looking for them, and as you mentioned, NEOWISE out there in the infrared band looking for them, how many asteroids are out there that are what we call near-Earth objects?
Well, so far we have found a little over 18,000 asteroids of all sizes that come near Earth's orbit. But we think that's a very small part of the overall population. Right now, our tasking is to find the 140 meter and larger asteroids that come near Earth's orbit. 140 meters, that's about 400 to 500 feet across. So we have several ground-based projects to do that. But our prediction on the population of those objects is 140 meters and larger in size is 25,000.
Wow.
So far, we've only found a little over 8,000 of those in the 20 years that we've been searching so far. So it's a very complex and complicated job.
Yeah, so this is a slow and steady process, but it's one of those that we got to keep doing each and every day, is finding these objects. And then you analyze their orbits to determine if they're really threats to Earth. So how many out there are really threats to the Earth?
Well, that's right. We have to take several observations over a course of time to be able to determine their orbit and whether they're sometime in the future going to come close enough to Earth to be an impact hazard. Right now, with the known objects, there are none that have a significant possibility of impacting the Earth. There are several that come very close, and if their orbits were to deviate off of our current predictions for them, they could be impact hazards. So there is a subclass of near-Earth objects, which we call the potentially hazardous asteroids, that we have to more closely monitor and keep track of those. We now have about 1,900 of those objects that we closely monitor.
Well, let's talk about one that flew by the Earth pretty recently. It's called Asteroid 2010 WC9. Yeah, so tell me a little bit about that.
Okay, well, by the designation, we know that this object was found originally in 2010. That's the 2010 part of the designation. The WC9 then tells us which month it was found in. Begins with a W, so we know that is at the latter part of November of 2010, and then 9 is a sequential number. It's kind of a complicated designation system, but it works for the astronomers.
Do we know if it was observed first by WISE or by ground-based, or how do we know?
Now, this was first observed by the Catalina Sky Survey in Arizona, and just a few observations were able to be taken of it in that time period in late November, first couple of days in December of 2010. So we didn't have a very good orbit on it yet at that time, and in fact, we couldn't project the orbit out more than a year or so with any degree of certainty.
So this close flyby is going to really give us a lot more information about it.
Oh, sure. So we knew it would have another close approach with the Earth at about this time frame, but we didn't know how close. In fact, the uncertainty and time span of when the close approach would happen was 18 days.
Wow.
Object moving at the speed it does covers a lot of distance in 18 days. The Catalina Sky Survey, though, again reacquired this object on the 8th of May and started taking observations on it again. The Minor Planet Center, where all the observations from around the world go to, was able to quickly correlate those observations with the orbit that they had on this object found back in 2010 WC9. So now we've greatly expanded the orbit span, the observation span on this orbit, and can much more accurately predict its orbit.
Yeah, better predict when it comes by the Earth again.
Right.
One of the really neat things about this object is that it passed under the Earth and the Moon. I thought all these objects had pretty much Earth-like or plane-like orbits.
Well, the vast majority of them do. They're close to what we call the ecliptic, the orbital plane of the Earth in the solar system. But there are quite a few of them that are on more highly inclined orbits. Their orbit plane intersects the Earth's orbit plane at an angle that we call the inclination. For this asteroid, its inclination of its orbit is 18 degrees, which is fairly high.
Yeah.
It makes it a little more rare.
How close does the sun does it get?
It actually goes in almost as close as Venus's orbit to the sun, and then goes back out to the main belt area.
Wow.
Beyond Mars.
Highly elliptical.
That's probably where it originated at some point, and some encounter with Mars or Jupiter along the way put it into this gravitational assist, put it into this more highly inclined orbit.
Yeah, so Mars and Jupiter in particular are throwing these objects out of the asteroid belt. So this is one of the ideas that tells us that we always have to be monitoring our skies and constantly looking, because the source region, the asteroid belt, is full of them.
Yeah, that's right. It's probably the remnants of a planet out there that either didn't form or got pulled apart by Jupiter, one of the two. And so Jupiter is always causing disturbances in the asteroid belt, and either flinging objects out of the belt and out of the solar system in some cases, or pushing them into the inner solar system.
You know, one of the other ways we use to not only characterize them but get a better orbit is through radar. How does that happen?
Well, we first have to find them optically. The radar is not, we don't have powerful enough radar that can sweep the skies and detect these objects. We have to have a good enough orbit that we know when to expect the energy back that the radar bounces off of the object, when to know that energy will return, because we got to dig it out of the noise. If we didn't know where to look, we wouldn't see it at all. So that's the first thing, is we have to get a good enough orbit on it with optical telescopes, so that we know where to aim the radar and when to expect the return.
You know, it also tells us a lot about its size and characteristics.
Right, with enough energy back bounced off the object, we can do what they call radar imaging. It's a little different than optical imaging, but it's sort of the same principle. And we can get a good indication of the size, much more precise than we can optically. And also its spin state, how fast is it rotating. And the other thing that radar does for us is determines whether these objects are binaries or even have more moons. We know of several binary asteroids now, an asteroid with a small moon circling it, and that's all been done by radar.
What's really neat about that, too, is if they get close enough to the Earth and the radar hits them, you can actually see features on their surfaces.
That's right. You can see craters or large boulders on the surface. It's really very interesting to see these radar images come back.
I mean, the concept that these things are still accumulating material, you know, and they're strewn with boulders on the surface. You know, we have a specific name for that. Yeah,
it's accretion of matter, and These are the remnants of the construction of the solar system. These are the building blocks. And, you walk around any construction site, you're going to see all this debris around. Well, that's what the asteroids and comets are, the debris from the construction of the solar system.
Yeah, actually, we call them rubble piles.
Well, that too, yes.
What kind of damage, if one of these larger objects would make it through the atmosphere and hit the Earth, would we expect?
Well, it certainly depends on the size of the object. This object, WC9, 2010 WC9, is estimated to be between about 50 meters and 120 meters in size. That could be a very damaging impact. For instance, the object believed to have created Meteor Crater in Arizona is estimated at only 50 meters in size. So that's at the low end of our estimate of the size of this object. It would devastate a statewide area if it were to impact.
But objects that are half that size, maybe 20 meters, do they make it to the surface?
Well, pieces of them certainly will. It depends on how strongly they're composed. If they are the average rocky asteroid, they will disintegrate in Earth's atmosphere. That, of course, recently happened in February of 2013 over Chelyabinsk, Russia. Object about 20 meters in size entered about 9 a.m. in the morning and detonated about 23 kilometers above the surface. The energy release was equivalent to about a half a megaton of energy.
I remember that day really explicitly. I was being interviewed on a variety of TV shows about another asteroid that was flying by the Earth, completely disconnected. And when this happened, we were all scrambling to figure out what was going on. Yeah.
Well, I remember that day well too, because we had predicted that 2012 DA4 was going to have a close pass by the Earth.
And that's the one we were talking about.
Yeah, just outside of geosynchronous. And actually, my community, planetary defense community, was at the United Nations Committee on Peaceful Uses of Outer Space meeting that week to provide our recommendations on what we as an international community ought to be doing about near-Earth asteroids. And we thought this close approach was going to be our signature event for that week.
Little did you know.
Well, Mother Nature has its ways, and Mother Nature just put an exclamation point on our report to the UN.
So, as you go to these meetings that are international and you talk about these as hazards and mitigation strategy, what can we possibly do on Earth to prepare to respond to these objects and over a certain size range?
Right. Well, as I said before, the first thing we got to do is find them. We've got to expand our capabilities to find them far enough ahead of time that we have a chance to do something about them out in space. Any object that's larger than about 50 meters in size, we're going to want to find years in advance so that we have a chance to do something about it in space, because we just don't want to suffer the impact from those objects. And so we also have to be looking at the technology that might be used. As I said, the principle to be used is you just need to change the speed of the asteroid by just a fraction of a percent to several years in advance to make it a miss instead of a hit. It will not arrive at the same time that the Earth is at that point in space. So that's a principle to be used. Now, if the object is small enough, just hitting it with a spacecraft, what we call a kinetic impactor, would be enough to change that velocity enough to slow it down. And in fact, we're working on a demonstration of that capability now. It's called the Double Asteroid Redirect Test.
Or DART.
DART, yes. And DART is about to enter its full-scale development phase.
Yeah, that's a really neat mission. Let's talk about DART a little bit. This is our first attempt to actually intentionally change the orbit of an asteroid, and it's going to a particular one.
That's right. We've chosen the target asteroid Didymos, actually the asteroid system Didymos, because Didymos is a binary asteroid. It is about a half a mile across the primary, and it's orbited by a moon that is only about 300 feet across. So with the DART spacecraft, what we're going to do is impact the moon and change its velocity in its orbit about the primary, so that will change its orbit, and we can observe that from the ground, from ground-based telescopes, observe the change
and radar
of the moon's of the moon.
Yeah.
Both optically and radar. Of course, radar will give us some more precise measurements and provide us the data that more precisely shows how much force we were able to impart on this moon.
Yeah, that's a really neat idea. If you hit that moon, you ought to be able to detect the change in its orbit much quicker than if that was a single asteroid orbiting the sun.
Yeah, that's right. And the other thing about it is that we're not changing the orbit of this whole system around the sun, so we're not increasing the danger to Earth of this asteroid.
You know, there are some things that, we just can't do much about. Climate gives us hurricanes and tornadoes, and, and there may be things in the future which, like asteroids that come in and impact the Earth, that means we wouldn't be able to move it in time. What are the things that we're doing now that could help everyone?
Well, that's right, and we are working with the interagency community, the U.S. government, to better prepare all of our activities if an object were detected on an impact trajectory. Yes, it might be something on very short warning and that we're not able to do anything about it in space. NASA's job, of course, would be to warn of it and predict how bad the effects could be based upon our observations of its size and composition. And we provide that information to other agencies like the Federal Emergency Management Agency, who would then be responsible, if it were to predict the impact in U.S. territory, for the safety of lives and infrastructure.
Yeah, it makes a lot of sense that we work with FEMA, who's a real expert in the ability to put out warnings and get the state and local governments to be able to help in getting the information out and people moved.
Yeah, it's been a real unique opportunity to work with FEMA, and FEMA, although that, of course, is their job, this is a little unique thing for them. This is probably the only natural disaster known of that we can predict, not only minutes, but days, weeks, or even years in advance. And so they sometimes wonder, what are we going to do with all that time?
Well, we're gonna get people out of the way if it does happen. But of course, that's just one of several things. As you say, the earlier the warning, the better. Are there other approaches that we're modeling or thinking about?
Right. Well, there are at least a couple of other techniques, we call them, that we think would be effective against an asteroid. Another technique that we've done modeling of and some development of the capability is called a gravity tractor. If you have enough time and the asteroid isn't too large, all you need to do is nestle up to it with the spacecraft, stand off orbit with it, and the mutual attraction between the spacecraft and the object by gravity will slowly tug that asteroid off its natural orbit into a new orbit. We're just using nature's tug rope, gravity, to tug the asteroid into a more benign orbit. That would take several months to years to do that. But the other nice thing about it is that we can put it into the new orbit, into the exact new orbit that we want to. We could tug on it a little while and then take measurements to see if we've changed the orbit enough, and if we need to do more, then we tug on it longer.
It's really amazing to think that just a few decades ago, we didn't really realize that how big a threats these kind of things could be in our future. But we're really evolving.
That's right. 40 years ago, the astronomers didn't know that there were very many objects in orbits that could cross the Earth. In fact, when the near-Earth object program started at NASA back in 1998, there were only 500 asteroids that were known that came inside of the orbit of Mars. Now we have 18,000 in our
still
catalog,
looking.
and still looking, and that's probably less than 5% of the population out there that could do damage to the Earth's surface were they to impact.
You know, the more we work in this area and the ones we find and then announce, it gets picked up a lot by the press. And of course, we're interested in being open, transparent, and telling everyone what's happening. But what do you think is the most common misconception that you see that the media or press do when they talk about these asteroids?
Well, I think because it is something that really sparks the imagination, and there have been these movies about asteroid impacts and those kinds of things, is that every asteroid that we announce is going to have a close approach. It sets off a concern that is this asteroid going to impact us? So I don't think they understand that once we have observations on the object and can establish its orbit, it's going to stay on that orbit.
Right.
It's just not going to wander around the solar system randomly. This is all controlled by the laws of nature, the laws of orbital mechanics. And once you've established a stable orbit, you can predict where that object is going to be many, many years in advance. Our current capabilities, modeling capabilities, we can confidently, given enough observations, predict the orbit out 100 years into the future to determine whether the object is ever going to be a threat to the Earth.
If our listeners could walk away with one lasting message, what would it be?
Well, I think the message is that asteroids can be a hazard to the Earth, are still impacting the planets. But we now have the technology and capabilities to find out if any of them are going to be a threat to us, and the spacecraft technology to go out and do something about it and prevent it. This is the only known natural disaster that we know that we could prevent if we know about it far enough in advance.
Yeah, that's really neat. One of the things that I ask each of my guests is about their gravity assist. And then that's the activity or event that occurred in their life that really propelled them forward to become the scientist or engineer they are today. Lindley, what was your gravity assist?
Well, gee, I've had so many of them in my career. I really have. I've been lucky, and some might say I've been in the right place at the right time on several occasions. I think the Apollo program when I was growing up, got me interested in space and being a part of the space program. That in turn got me interested in being in the Air Force and being part of the Air Force's space program. That gave me the capabilities, the skills, because of the opportunities I was given and the trust that was given in me to really develop my capabilities for program management and looking forward into the future with these kinds of things. Then coming to NASA 15 years ago now, and being put in charge of this program, this Near-Earth Object Program called back then, and also working with the solar system exploration missions, has all given me the skills and background to be NASA's first planetary defense officer.
Lindley, I've known you for a number of years, and I can attest that you are absolutely the right person for this, and I am so delighted that indeed we can look to you as our officer of defense for this planet. And I want to thank you for all the hard work you've done over the many years.
Yeah, well, thank you for this opportunity and the years that I've worked with you in the Planetary Science Division. It's been a real highlight of my life.
Yeah, I've enjoyed it, and it has been one of mine too. Well, join us next time as we continue our exploration of the solar system. I'm Jim Green, and this is your Gravity Assist.